Yes. Good morning. Welcome to the next session of module number 2, that is limit state analysis of beam. Okay, in the last sessions we were discussed regarding singly reinforced and doubly reinforced section. So as I was explained in first session that we are going to deal with three sections or three types of beams in the module number 2. We have come across singly reinforced section or singly reinforced beam analysis we did. Next we discussed doubly reinforced beams and we have done the analysis of doubly reinforced beams. Next is we are going to deal with the flanged sections. Flanged section. So let us get into this. What exactly is flanged sections? Okay, and its stress block parameter and what will be its analysis part, and later on we will go with the analysis. Okay, so coming to the flanged sections. Okay, so this is the typical 3D view have been written. Okay, so you can see here, so this particular portion will be called as slab portion, and this slab portion is resting on a beam, and in this particular thing you can see this corner portion which will be resting on a wall. Okay, so this is what the actual scenario you people are going to see when you're going to observe the roof. Okay, on the end of a slab which will be resting on the wall, and then in the middle portion it will be resting on the beam. Okay, so here the main thing you can see here in the flanged section, okay, which is also called as a T section and L section. Why? Because you can see over here this slab and a beam, are casted monolithically. Now you may start asking a question. Till now we were dealing with a rectangular section. We were dealing with this particular section. So now one more portion or one more component is added to the beam. Okay, so that means this monolithic structure. Why it is called monolithic? Monolithic I am going to call because the slab and a beam we are going to cast it together. Why? Because whatever the capacity or the moment of resistance of a rectangular beam, okay, those deficiencies we can overcome or we can enhance. We can enhance the moment of resistance of a section by this particular flanged section. Okay, so we can overcome those, okay, what I can say, the difficulties, okay, because the moment of resistance of a rectangular section will be less, the structural behavior will be less. In order to overcome these, okay, or to enhance the structural capacity, we are going with the flanged sections. Is it clear? Fine. So now, since I have been told these components are casted monolithically, okay, because by monolithic casting, both the slab and the beam will act like a one unit. That is what the advantage of casting monolithically. Okay, the slab and the beam will act like a one unit. Okay, then coming to this you can observe, okay, you can observe the figure 1, okay, if this particular whatever the section is there, okay, this particular, okay, that has been bifurcated or I can distribute it on either side. Okay, that are distributed on the either side. Okay, so then this particular thing is called as T section. Okay, so I'm going to repeat. Okay, if the flange projection, or I can say if a flange projections are on either side, if the flange, so this portion is called as flange. This portion, the slab portion is called as flange, and the beam portion is called as web portion. Okay, and you people have come across this type of sections in your engineering mechanics class. So there you people have done only how to calculate the neutral axis. But in this case, apart from neutral axis, we are also going to deal with the analysis. That is, moment of resistance you are going to calculate. Okay. So now this portion is flange portion and this portion is called as, okay, web portion. That is, the slab portion is flange portion and the beam portion is a web portion. So now, if this slab portion or flange portion having a projections on either side, okay, if the flange projections are on either side, so this particular thing is called as T section. Okay, T sections. Okay. Next, if the flange have a projections on one side, if the flange has a projection on one side, it is called L section. So that means the flanged sections or flange, okay, beams are also called as T section beams or L beams. So that depends upon the sections you are going to analyze. Okay, the middle portion will be T, the corner portion will be the L sections. Okay, and why these particular sections or flanged sections are required? I already been told, in order to enhance the structural capacity. Okay, the moment of resistance of a flanged section will be more than that of a rectangular section. Okay, and these particular flanged sections are commonly used in practice compared to rectangular section. And whatever you people are seeing on the roof, okay, it will be acting like a T-beam. A very simple example you can see on the roof, okay, whatever the beam that is running, okay, that will be the web portion, and the slab resting on the beam is called as a flanged portion. And both these beam and slab, I think you may be observed in your construction practice, okay, when they are going to cast the slab or when they are going to pour the concrete, those concrete will be distributed to the beam also. Hence, the slab and beam will behave like a monolithic units or monolithic structure. Hence, it is called as T section and also L sections. Is it clear? Okay, so this is the one part of a written, okay, and you can see the 2D diagram also been written. Okay, the same thing have been taken. See, this will be the width of a flange, that is BF. Okay, and this will be your width of a web. So this will be your width of a web. So that is called BW. This is a flanged portion and this is a web portion. Is it clear? Slab and a beam. And this corner, that is L section, you can observe on the roof, will be resting on a wall. So this will be the wall. Okay, and the next, okay, I have taken the middle portion of a flanged section, that is a T section. That means the flange having a projections on either side. Okay, if I am going to take, okay, this will be your width of a flange because this is a flanged portion and this will be your web portion. Okay, and this will be the depth of the flange and this will be the width of the web and this will be your depth of the web. Okay, so these are all the components of a flanged sections. It may be T sections or it may be L sections. Both the things we can come across. Okay, and a very important thing we need to note over here is the notations. The depth of the flange, the width of the flange, depth of the web. Okay, all those things are very, very important. Okay, so these are all the things and the advantages have already been explained. So since I am going to cast it monolithically, okay, the structural capacity of a flanged section is more than the rectangular section. So hence commonly we are going to use these type of flanged section, okay, more in the practice. Okay, so this is regarding the introduction part of a flanged section. So hence this flanged section is also called as T sections or L section geometrically, I can say. Geometrically the flanged section is also called as L section and T sections. Is it clear? So this is regarding the introduction part. Hope it has been clarified. Okay, I have been explained what is flanged section. Okay, what are all the notations. Okay, all those things have been explained. Okay, and the advantages. Next, coming to the stress block parameter of the same flanged section. Because in the singly reinforced section and the doubly reinforced section, we come across the stress block parameters for the same singly reinforced beam and the doubly reinforced beam. Here also the stress block parameter for the T sections have been considered the flanged sections. So consider the flanged section or a T section whose width is BF, that is BF because this is a flanged portion, this is a flanged portion and this is a web portion. So this will be your BF, that is width of the flange. This will be your DF, capital D. Please note down all these things. That is small bf, width of a flange, capital DF, depth of the flange. Next, and this will be the width of the web, small b suffix W. And the next, the same thing, effective depth. Same thing, it remains same. It is the distance from the extreme compression fiber to the centroidal axis of a tension steel. Okay, and this particular zone is called as compression zone. Okay, the slab portion is called as compression zone. Okay, next. So the neutral axis, the very important thing, the neutral axis. I think you might have been done the neutral axis in your elementary classes, that is in first sem or second sem. Okay, there you people know that the T section is symmetrical about YY axis. It is symmetrical about along YY axis, but it is not symmetrical along XX axis. It is not symmetrical along XX axis. Hence, the neutral axis will not lie exactly at the center. It will lie somewhere at the in the portion, neutral axis. So that is very important. We need to find out that. That is what very important in this analysis. XU. We need to find out whether the neutral axis is lying within the flange or outside the flange. That is what the aim of a problem. Okay, we are going to come across a two condition here. In the analysis of a T-beam, we are going to come across whatever the neutral axis we are going to calculate, whether it is going to lie within the flange or outside. That is what the thing I am going to explain in the next session. Okay. Next, here the same thing, the area of steel that remains same, no change. Okay. Now, if I am going to draw the stress block parameter for this, so now you can observe this particular first thing. Okay, it will be combination of rectangular and parabolic. It will be the combination of rectangular and parabolic variations. You can see till the DF, or I can say till 0.43 XU max. Till the distance of, this will be your XU max, that is maximum depth of neutral axis. Okay, till 0.43 distance of XU max, it will be rectangular variations. Where your compression force 1 will lie. Because C1 will be lying at edge. Okay, and another compression force will lie at the middle portion. So one particular compression force will be acting C1 exactly at the edge of a rectangular portion or end of a flanged portion, okay, at a distance of 0.43 XU max. And this remains same, that is 0.45 FCK, this you already know. Okay, and the next, the T1, that is tensile force carried by the steel. Okay, now come to the another thing. Okay, so this once again, this is from C1 to the neutral axis portion, it will be parabolic variation. That means this rectangular section, okay, or rectangular portion will be the parabolic variation. And the next, you can see the same rectangular portion with a DF. Okay, one more compression force, that is C2, will lie exactly at the center of a flange. Hence, the depth of this particular C2 will be 0.5 DF. The compression force C2 will be acting at exactly at the middle, that is 0.5 df, and once again this remains same, 0.45 fck. Okay, next, and the C2 distance, okay, from this particular end to the centroid of the tension steel is equal to d minus 0.5 df, because you already know it is d minus this distance will give you the d minus 0.5 df. So this is the stress block variations of a T sections or a flanged sections. Okay, hope you know that. So this particular thing, okay, that is flanged portion, I am going to divide it into two compressive forces. One will be acting at the edge and another will be acting at a middle portion. And those corresponding distance have been noted. Okay, and this is what the stress block parameter for a T section. Is it clear? Now come to the analysis part, a very important thing. Okay, now I will consider the same T section with the same width of a flange, depth of the flange, width of a web, and with the area of a steel and effective depth. I have considered the same diagram. Okay. Now this T section I am going to analyze, I am going to divide it into two sections. I am going to divide it into two sections. Okay, you can see here the one portion, okay, I am going to treat it as a rectangular portion. That means whatever the web portion will be there, that will be extended till the flanged portion. So that is what a rectangular section have been written. Rectangular section have been written. Okay. So whose width is same thing, BW, and it will carry AST1. Let me call this as first section. Okay. Listen here. So the web portion I am going to extend till the flange portion. Take out this component rectangular portion. Let me call this as section number 1 with a width BW. With a width BW with AST. This is what a first section. Next, in this overall T section, deduct this portion. Deduct this portion. The left out portion will be two rectangular box. Two rectangular portion. So that is what I am going to represent. Okay. So this will be your rectangular box. Okay, and this will be the semi-solid line. Okay, semi-solid line that is in, okay, not visible. Okay. So next, the width of this portion will be, listen here, the total distance will be BF. Okay, if I am going to deduct this, the left out will be BF minus BW. Since the two portions are there, BF minus BW by 2, and then here also BF minus BW by 2. And it will also carry the additional steel or AST2. Is it clear? So like this I am going to analyze. Okay, and the very important thing we are going to do in the analysis is whether the neutral axis, that is XU, the distance XU, okay, whether it will be lying within the flange, that is XU, okay, this XU distance, okay, or here XU distance, whether this XU, okay, lying within the flange means obviously, so this XU will be here, XU will be here, okay. Obviously your XU will be lying. That means the XU is lesser than or equal to DF. This is one analysis part we are going to do for a flanged section or T section. XU lesser than or equal to depth of the flange, or neutral axis is lesser than or equal to depth of the flange. That is one analysis. Okay, we need to check that. Okay, now the next one more thing is, if XU lies outside, we need to calculate at XU. If XU is greater than DF, then the analysis changes in a different way. Okay, we need to check that. So depending upon that XU and DF value, that is XU lesser than DF or XU greater than DF, we need to calculate the moment of resistance of a section. The aim of the problem remains same, no change. In singly reinforced also been calculated moment of resistance of a singly reinforced. In doubly reinforced also have been calculated the moment of resistance. Here also the same thing, we are going to calculate the moment of resistance. The thing is, we need to calculate first XU. We need to check the conditions, whether the XU lesser than DF or greater than DF. Is it clear? Is it clear? Fine. So next, this is regarding your introduction part, stress block parameter and analysis part. Hope the concepts are clarified. Is it clear? So now let us know, okay, or let us proceed how to calculate the moment of resistance for a T section. For a T sections. What is the steps we are going to follow? Okay, let me go ahead. Now, let me go with the first one, that is steps for calculating the moment of resistance. Steps for calculating the moment of resistance for flanged section. For flanged section. Okay, the first is case number 1. Case number 1. Let me go with the first case, that is neutral axis lies within the flange. Neutral axis lies within the flange, that is XU lesser than DF or equal to DF. So this is the first case. For this particular case, okay, how to calculate the moment of resistance? Okay, so for this, let me write down the diagram first. Okay, this will be your width of the flange, this will be your depth of the flange, this will be your BW, okay, and the next, let me provide with the 3 number of steel, okay, and let me call this as effective depth D, okay, and the very important thing is XU, okay, and this XU is lying somewhere here. Let us assume that your XU is lying within the depth of flange, that is XU lesser than DF, okay. So for this, okay, let me go ahead, okay, so I will write down the thing. So first, let me calculate, okay, the depth of neutral axis. First, we need to check, okay, whether the assumption which have been made, that is XU lesser than DF holds good or not, okay. Whatever the assumption have been made, okay, whether it is correct or not, that I am going to check now, okay. So step number 1 we are going to do is calculating the depth of neutral axis, okay. How to calculate this depth of neutral axis? The same thing, okay, as per annex G 1.1a, page 96 of IS 456/2000. The formula is XU by D is equal to, okay, the same formula, XU by D is equal to 0.87 Fy into AST divided by 0.36 FCK into BD. So from this you are going to calculate the XU. You are going to calculate the XU. Okay. If XU calculated is lesser than or equal to DF, whatever the assumption have been made is correct. Okay. Whatever the assumption have been made is correct. Okay. Because I have assumed that XU is lesser than DF or equal to DF. Okay. That assumptions holds good. That assumptions holds good if the calculated value of XU is lesser than the depth of the flange. You can see that B is, you can write down width of the flange, okay, DF, depth of the flange, next BW, width of the web, next D, effective depth. Okay, so all these things. So these are all the notations. Next, so after calculating this, if assumption is correct, if whatever the assumption have been made is correct, then proceed with the next step, that is maximum depth of neutral axis. Okay, so maximum depth of neutral axis, okay, no change. Okay, the same thing we are going to follow. Refer note, okay, of page 70 of IS 456 2000. Okay, refer note, okay, of page number 70. How? Okay, that means based upon the grade of a steel or yield strength of a steel, we are going to pick up the XU max by D value. So that is what the thing. Next, okay, step number 3. Step number 3, that is deciding the section. Deciding the section. Let me write down here. Step number 3. Okay. So step number 3 is we are going to decide the section. So coming to the first case, if XU is lesser than XU max, what you are going to treat? The section is under reinforced. The section is under reinforced. So for this under reinforced, how to calculate the moment of resistance? Moment of resistance, let me write down the same formula, that is as per Annex G 1.1b, that is 0.87 into Fy into AST into D 1 minus AST into Fy divided by BD FCK. So this formula you are going to use, and this will be from Annex G 1.1b. 1.1b. Okay. Next. So by this we are going to calculate the MU. Next, if the XU value, that is depth of neutral axis, is more than XU max. If XU value is more than XU max, then what you are going to do? Then the section will be treated as over reinforced section. The section will be treated as over reinforced section. How to calculate this? So then we are going to limit the moment, that is MU lim. MU lim. Okay, where this formula? Annex G 1.1c. Annex G 1.1c. That is 0.36 XU max by D. 0.36 XU max by D into 1 minus 0.42 XU max by D into BD square FCK into BD square FCK. So this is the formula you are going to use. So this will be there in the annex G 1.1c. That means whatever the analysis we are going to do for a T section, okay, that is XU lesser than DF, we are going to treat it as a singly reinforced section. We are going to analyze it as a singly reinforced section. Whatever the thing we have did for a singly reinforced beam, the same thing holds good here. Okay, so that is if XU lesser than or equal to DF for this condition, okay, calculate the XU value, then calculate the XU max value, then cross, that means compare this or decide it whether it is under reinforced or over reinforced. So after deciding under reinforced, calculate the moment of resistance if it is under reinforced like this. Calculate the moment of resistance if it is over reinforced like this. You may use this formula or you may use different formula, that is depending upon the grade of steel. That is for mu lim is equal to 0.148 FCK BD square for Fe 250 steel. You can use that formula also. Mu lim is equal to 0.148 FCK BD square. Next, this is for Fe 250. Okay, like that. Okay, for 415 you have 0.138 FCK BD square. Okay, next for 500 0.133 FCK BD square. You can use these formulas. Okay, you can use this formula or you can use these formulas to calculate the ultimate moment of resistance for a T section. Is it clear? So this is what the step we are going to follow for our calculation of moment of resistance if the assumed neutral axis is lesser than or equal to DF. Next, case number 2 will come, okay, if the assumption is wrong, that is if XU greater than DF, how you are going to follow the steps to calculate the ultimate moment of resistance. So that I will be discussing in the next session. Okay, so hope you have understood whatever I have been discussed in this particular section. We have been discussed, okay, what is flanged section, okay, and this advantages of flanged section. Next, we have come across stress block parameters and we have discussed the analysis part, and next in analysis how to calculate the moment of resistance. So these are all the things we have been discussed. So in this continuation, this, okay, that is XU greater than DF, we are going to discuss in the next class. Thank you.